Okay, so welcome. We made it to the last lecture of this semester. And really the meeting today is off schedule. The plan is for you to ask questions. So please feel free to do it. What I planned for today is basically to remind you what we've done since the midterm. So I prepared a very, very short review. So really it's up to you if we want to spend or how much we want to spend on each topic. So anyhow, so let me start by reminding us of some of the admin stuff. Importantly, homework 5 is out. We gave an extension. You can check the syllabus, the website, until next Tuesday, which is December 15. But there's no additional Slack time, so that's it. So that's a hard deadline because we want to put the solutions out. So remember that, tell your friends who are not here. Final, I guess you all know that by now. Next Friday. One important issue that I'm going to also put on Piazza is that you know the time, you have 12 hours and you're going to do this somewhere in this time window. But you only have 90 minutes within this time window. I'd like you to open your video when you're doing the exam. If you have any problem with this, let me know. But other than that, I'd like it to be open. I think that's about it. Oh, one additional issue is extra time. So some of you deserve extra time to take the exam. If you are one of these, please drop me an email. I'm assuming by default that it's going to be exactly like the midterm, but would be good to get confirmation. Okay, I also put here the project's information, but there's nothing new here. Okay, so you are supposed to be on a Zoom link. We are going to send a separate Zoom link for the exam. Yes, so you are going to do the exam on Zoom if it wasn't clear. Thanks for the question. The final is just like the midterm, open book, open everything, yes. Other questions pertaining to the admin of the final? Okay, so what I want to do is basically review what we've done. Hopefully this will remind you some of the things and will trigger some questions. If not, we're going to finish this meeting very quickly. So this review, okay, so in fact, before I start the review, I want to remind you something that I said, I think in the first lecture of this class, the first introductory lecture, which was, it's an applied machine learning class. And really, what does it mean applied? So most of the applied came in the homework. Hopefully you've learned a lot from doing the homework. And the machine learning part is mostly in the classes, in the class, in the meetings, in the quizzes, and in the exams. So there is some separation that is necessary by the nature of the class, and the exam is going to focus on the machine learning. Maybe a little bit on some lessons that you've learned from the homework, but we basically decouple the homework from the machine learning principles that we learn in the class. With that, let's see. So basically, I put one slide here for each one of the lectures or the units that we've done since the midterm, just as a way to remind ourselves what we're doing, what we've done. So this the first unit after the midterm was devoted to learning theory. So basically trying to understand why do things work, when do things work, what are the complexity parameters that learnability depend on. So we basically talked about PEC learning, probably approximately correct learning as the main framework. And in this context, we talked about Occam's razor. So we basically showed that simple is good. Small hypothesis spaces are good. We started by doing it in a simple context of consistent learners that make no mistakes on the training data. They can actually derive a hypothesis that is perfect on the training data. And then we showed that in these cases, as a function of the size of the hypothesis space, it's going to be good also on the test data. Then we generalized it, or at least we said that we generalized it. We didn't give the proof to the almost consistent case. And we showed the relations between error on the training data and error in the future on test data. And we also talked about the assumptions that are underlying all this theory. We then moved to the infinite case, right? So everything at the beginning was with a finite hypothesis space, but then we moved to the general case, and in order to do this, we introduced this notion of VC dimension, and essentially show that this notion captures the complexity of the hypothesis space, and therefore it can be thought of as replacing the log of the size of the hypothesis space. So what I show here on the slides is essentially the two types of bounds that we derived. So in one case, we related the two types of error, the error on the training and the true error, the error on the distribution, using some term that depends on the size of the hypothesis space, the number of the examples, and the delta, the confidence parameter. In the second case, it's really the same kind of bound, but in this case, I'm viewing it from the perspective of the number of examples, M, that you need to see in order to guarantee a specific level of error, epsilon. And again, it depends on the size of the hypothesis space. So really, learnability depends on the log of the size of the hypothesis space, or in the infinite case, on the VC dimension. Questions on this? Okay, section 2. SVMs. So SVM is one of the most important algorithms that we've seen in the class. Still a very important algorithm, even though the wind is kind of moving for, and more people want to use deep networks, at least today. We don't know what's going to happen in 2 years. And we talked about several of the theoretical underpinnings of support vector machines. Why does it make sense? How do we derive it? And the key concept that we talked about in this context is that of margin and maximal margin. We talked about the relations between maximal margin and VC dimension. Really, VC dimension theory is the driving force behind this algorithm. because we know that we want to minimize VC dimension, and we are asking, how can we do this algorithmically? From the relation to VC dimension, we move to the relation to the size of the weight vector, W. And we show that maximize the margin means minimizing the size of the weight vector. In doing that, we had to deal with a lot of subtleties of what does it mean to minimize the size of the weight vector? Can't you just multiply everything by a small constant and the size of the W is going to go down? So we dealt with these issues and said and showed that, there are really equivalence classes of weight vectors. And we need to take a representative from each equivalence class and then think about what it means to minimize the size of the weight vector. So with these discussions that really required you to understand some linear algebra, we talked about the optimization problem underlying support vector machines. We started with the hard SVM optimization, and then we moved to the soft SVM optimization. So what I show here on the side is in the top slide, the notion of margin, the fact that the line in the middle is the linear separator, the set of all points x such that wx plus b is equal to 1. And we normalize everything so that the two lines parallel to it here, one of them is wx plus b equal to 1, and the other one is wx plus b equal to minus 1. And we do it such that in the hard case, the closest points reside on these two lines, the wx plus b equal minus 1 and plus 1. And then we relaxed it and we moved to the soft SVM formulation where we allowed some slack parameter that really reflects the error. So when we talk about, when we look at it this way, we derive this formulation that allows us to also, in an explicit way, think about the distinction between error, the empirical error of the classifier, which is what we see on the right, and the regularization parameter, how to guarantee that the hypothesis is simple. And really what we want is a combination of both. Okay, so we have a question here. Why the max margin is related to the VC dimension. So what we've shown, and we can see this in this picture here, is so VC dimension, the way we defined it in the previous slide, in the previous unit, is something that is associated with the hypothesis space. So you can think about the hypothesis space of all linear separator in n dimensions. We actually explicitly showed it in the case of the plane in 2 dimension and showed that the VC dimension is 3. In general, if we have an n-dimensional space, the VC dimension of linear separator is going to be n plus 1. Now, that isn't sufficient even to make the distinction between these two cases here, where I have a linear separator that separates the blue from the red with a very small margin, and I have a linear separator on the right that separates the red from the blue with a large margin. Of course, we want to prefer the one on the right, and the question is, how do we do it? So we refined the notion of VC dimension to be data dependent and said that I'm going to define a class of functions, linear separators that separate the data with a specific margin. So it's a hypothesis space that is parameterized by this margin, by this gamma. And then we quoted a result that said that the VC dimension of this class of all linear separators that separate the data with a margin of gamma is proportional to 1 over gamma squared. which means if you have a class of functions, if you can separate the data with large margin, the VC dimension is going to be smaller. Again, the VC dimension of H subscript gamma, the set of all functions that separate the data with margin at least gamma, is 1 over gamma squared. So we quoted these results, and that motivates us to find a hypothesis that separates the data with a large margin. This relation to minimizing the VC dimension was the motivation to basically to the support vector machine. So go back to these lectures and you'll see that we basically started with these results. It's a result by Vapnik that I just quoted, the relation to VC dimension. And from that we derived, and that we actually did, the relation to the size of W. So there are really 3 steps. I want a small VC dimension. Because of that, I want to maximize the margin. And the way I'm going to do this algorithmically is by minimizing the size of W. So that's actually a very important kind of 2-step process that we discussed. And if you go back to the slides, hopefully this will be clear. That allowed us to, as I said, to define these optimization problems, define the notion of regularization, which you can see here in the lower slide, this notion of I want to minimize the size of W. Dot product W transpose W is the size of W, the L2 size of W. And we've seen this many, many times since then. The idea that we want to minimize empirical error and we want to keep it simple. We then talked a little bit about dual and primal, a notion that we introduced earlier in the context of perceptron, but we introduced it again or mentioned it again in the context of SVM and similarly kernels. One of the interesting things, I hope, was that we eventually showed the relation between SVM and perceptron, right? So you can see again, you can see it here. The type of loss that you have here is what we call the hinge loss. I point to it here with the arrow, with the blue arrow, which is the same loss that we showed earlier drives perceptron. And then we talked about multi-class SVM in the next lecture, but I mention it here because we define a notion of margin that generalizes the notion of margin that we started with here from the case of binary classifiers to the case of multi-class classifiers. Questions on this? Okay, so let's move on. The next step was boosting. And in the same unit, we also talked about ensembles in general, and then on multi-class. So boosting is interesting for multiple reasons. Originally, it was interesting because it was a really not only cool applications of learning theory, but also very practical applications. It's all started with a theoretical question about the relation between weak and strong learnability. Strong learnability is the standard learnability that we talked about. Weak learnability is just the notion that all I care about is that epsilon is going to be above chance, bounded away from chance. And so it started with this theoretical question and developed into a very practical algorithm that still today is one of the best, if you want, general purpose algorithms that we have. But I use this unit to discuss the notion of error in learning because it's a very fundamental issue. It's important to understand that error is a function of the distribution you're dealing with, and boosting, and specifically AdaBoost, exhibits that in a very, very clear way. The toy example that I show one slide of here is a good way to understand this, right? We basically have 10 examples in all cases, but the error is different each time because the distribution over these 10 examples is different. And changing the distribution this way forces the algorithm to focus on different examples every time, and therefore derives a different hypothesis every time. And altogether, when we put them together into a linear sum with the appropriate weights, we get a very good classifier. So this notion of distribution dependent, changing the distribution, why does AdaBoost work? And even the proof that took us about 3 slides is very insightful because it really forces you to think about a notion of distribution, notion of error in learning, and so on. So from that, we move to talk about boosting, bagging, and random forests, which are conceptually somewhat similar to AdaBoost in the sense that you have a collection of weak learners that you typically put together via a linear function, kind of like what you did in problem set 1 already. Each one of them is somewhat different and comes with somewhat different justifications, but we put them into one collection of ensemble method. We then moved on to talk about multi-class. There's many things one can say about multi-class. We only talked about 3 issues. We distinguish between the one versus all protocol and the all versus all protocol. And then we talked about a global multi-class. By global, I mean here that unlike the one versus all, and also the all versus all, where you make updates to your model as a function of what this label tells me, in the global multi-class, we actually make updates as a function of all the data and all the labels. So specifically, we talked about SVM as a global multi-class, and we generalized the optimization problem of SVM to the case of multi-class, basically by generalizing the notion of margin. Yes, so these review slides are going to be published. In fact, they are at the end of the previous lecture, the Bayesian networks lecture. I'm going to post it after today on the slide on the website again, and that allows me to remind you after every class I post the lectures. So if you looked at printed or looked at the lecture notes earlier, please go back and look at the lecture notes again, because there could have been some updates and some typo corrections and other clarifications. Questions on this unit? Okay, so let's move on. The next one was neural networks. Surprisingly, there's actually less to say about neural networks than many of the units, because a lot of it is basically just building models. But the key issue that we have to understand about neural network is how to learn. The basic rule you already know, it's gradient descent. Gradient descent with respect to various loss functions, and gradient descent with the ability to propagate it down to additional layers of the network. So we talked about the expressivity of neural networks, the fact that we derive power from the fact that it's nonlinear, the units are nonlinear, the fact that we want the units to be differentiable or almost differentiable so that we can propagate weights. And then we derive the backpropagation algorithm, which is the key tool that we're using in all architectures of neural networks. And then we talked about, very important additional architecture. So the backpropagation was derived in the context of feed-forward networks, or multi-layer perceptrons, sometimes called MLPs. But then we talked about two other important architectures, convolutional networks and recurrent networks, and some of the kind of more recent developments in each one of these, including mention LSTMs and attention, and the use of those to learn embeddings. Questions on this? Okay. Then we move to the last chapter of this class, where we talked about Bayesian learning. So the first step was to just talk about Bayes rule and the Bayesian learning scenario. Really, really important, really simple conceptually, but and in fact drives everything that we said in the next 3 units. Everything is based on Bayes rules. So you want to understand this, and you want to understand the learning scenarios. And we gave a few examples, and some of them you've also been playing with in the homework, so you've seen additional scenarios. As I said, everything is in this slide, right? So the idea that we use Bayes rule as a way to choose a hypothesis, or as a way to choose parameters, or as a way to make classification is the same every time you apply it for a different probabilistic model. So very, very general theory. And then we moved to one key application, which is classification, right? So we want to learn classification. So the classifier we talked about is the naive Bayes classifier. It's really naive, as we agreed. We understood the independence assumptions underlying it, really a crucial issue. But beyond that, we understood why does it work? And we linked that back to learning theory that we've done earlier by showing that if we really think about the decision rule, and that's here on the right slide, if we really think about the decision rule that naive Bayes works by, it's a linear decision rule, where the weights are essentially statistics over the data. That allows you to very quickly compute this linear separator. But on the other hand, it limits the expressivity of it. So it's not necessarily the best classifier you have, even though in practice, quite often it's pretty good. This allows us to relax a little bit the assumptions and move to another probabilistic classifier that is learned in a discriminative way. We call this logistic regression. It uses the logistic function just like the naive Bayes does here, only that it derives the weights in an optimal way. That is, or almost optimal way. It basically tries to find the best weights to minimize this error defined by this loss function. This algorithm is called logistic regression. And it allows us also to close the circle here, because we realize that now, especially if we are willing to add the regularization terms here, we are very, very similar to what we've done before, for example, with support vector machine. It's the same or very similar optimization problem slightly different loss function, but if you look at the graphs of the loss functions, you see that they are actually not that different. So logistic regression and support vector machines are very, very similar algorithms. There's a question here. Could you view naive Bayes as a two-layer tree-dependent distribution? Okay, let me do this in the next slide when I get to yeah. So let's skip this. I'm gonna review this when we get to tree-dependent distribution. Remind me if I neglect to respond to this. Questions on this: naive Bayes, relations to logistic regression, Bayesian learning in general. Okay, so the next step we've done is we relax the learning scenario a little bit. So everything we've done in the class so far has been supervised learning. And while this is definitely the most important learning paradigm, we have to, realize that we don't always have good annotation, complete annotation. And in fact, one of the hot topics today in machine learning is how to deal with these, I'm going to call them low labeled settings of learning. So we just touched upon this a little bit when we talked about semi-supervised learning. So the idea there has been assume that I have some labeled examples, but not a lot. But I do have a lot of unlabeled examples. Can I use the unlabeled examples as a way to improve my classification? So we started by talking about it in the context of naive Bayes, just because it's easy. And it also allowed me to move from there in a smooth way to talking about EM, which requires probabilistic assumptions. And in the context of naive Bayes, we said, well, we can do this, right? So we can learn from a small number of examples, take the hypothesis that we got, and use it to label the data that we have, but it came without labels. Label it, put it into our collection of labeled examples, and keep on going. And we talked about several scenarios or several ways to do that. And the key one that was the most general and most interesting was the one where we labeled example with fractional labels. We say this example is 0.6 positive, 0.4 negative. Now, from the naive Bayes perspective, it doesn't matter. Naive Bayes doesn't care whether the labels are integers or fractionals. But this gives us a lot of power. It gives us the ability to automatically care more about confident labels and care less about those examples that are not labeled with confidence, and also gave us a good step toward the next step, which is I'm going to drop the labels altogether. So I'm going to be in a case of missing data. Specifically, we talked about the case of missing label. And this is the context within which we developed the EM algorithm, expectation maximization algorithm. And we talked about it first in the case of Bernoulli distributions, the coin tossing example, where basically the scenario is that of a mixture of distribution. By mixture, I mean here that I have two coins. I can have 7 coins for the same price, but we dealt explicitly with the case of 2 coins. And when I'm told to use coin 1, I'm tossing it m times. When I'm told to use coin 2, I'm tossing coin 2 m times. And in addition, there is another coin, we called it coin 0, that mixes them. I flip coin 0, and if it's head, I'm tossing coin 1. If it's tail, I'm tossing coin 2. So we wanted to understand how can we, with this missing information, no one tells me which of the coins, 1 or 2, is being tossed to generate each sequence. How can I figure out what are the parameters of coin 1, coin 2, and the mixing coin? So we derived this EM algorithm that has 2 steps. The first one is the expectation step, which essentially is, if you want, the naming of the coin step. And we have to make some guess, initial guess, and given this guess, we can name the most likely label of each coin or the distribution. Again, we are dealing with fractional labels here. What's the probability that this sequence came from coin 1? What's the probability that this sequence came from coin 2? With this, now we have label data. We can try to find the most likely, to express the likelihood of this data, given the parameter, and find the maximum value of the parameters, or the values of the parameter that maximize this likelihood. And we know how to do this. Once you have an expression for likelihood, you know how to derive the parameters that maximize this value. In the specific case of EM, we had to, the math was a little bit more complicated because we didn't know exactly how to maximize the likelihood. We had to maximize the expected likelihood. And we did this by writing an expression for the expected likelihood and then differentiating it relative to the parameters. And that gave us these update rules that I'm showing here. We did exactly the same thing in the continuous case, where I have points that are drawn based on a Gaussian distribution, but again, based on a mixture of Gaussians. So I have 2 Gaussians, one with mean mu1, another one with mean mu2, and a point is drawn according to one of them, but I don't know which. And my goal is to figure out which Gaussian generated each one of the data points I see. So it's really the same algorithm. Again, I'm trying first to name each one of the data points. These are the PIJs here. Once I name each one of the data points fractionally, I look at all the data, I compute the likelihood of the data or the expected likelihood of the data as a function of the parameters, and then I find the value of the parameter that maximizes this likelihood. And that gives me the next muse, and I can keep on going. So the reason this works, it seems kind of magical, is that one can show, and we did not show that if you start with a guess, you compute the likelihood of the parameter or of the data, and now you replace the guess by the value of the parameter that maximizes this likelihood, the likelihood of the data. The next set of parameters gives rise to a better likelihood of the data. So you start with some set of parameters. You can compute the likelihood of the data given this set of parameters. It's going to give you some value. And then you take the expression for the likelihood, you find the values of the parameters that maximize this. With this set of parameters, you get better likelihood. And if you do this repeatedly, you're going to converge to a local maxima of the likelihood. We don't have guarantees that it's going to be global. We have guarantees that it's going to converge to the local maximum of the parameters. And then if we do this with multiple restarts, eventually we're going to get to good parameters. Questions on this? Okay. Last unit, we talked about Bayes nets. So the first issue that we dealt with is how to represent distributions. Again, now we are completely off to unsupervised learning. We just have data. We don't have a notion of labels. We don't care about classification. We just care about learning something about the data, computing the probability of events, given observation or just unconditional events. So looking at data, we want to be able to induce a representation of the distribution so that later on we can compute probabilities of events. What we've shown, and this is completely analogous to something that we've said throughout the class, even in the discriminative case, is that we have to make assumptions. If we make no assumptions, there are way too many options, and we're not going to generalize. So the assumptions in this case are in the form of independence assumptions on the distribution. So we talked about specifically the language of Bayesian networks, which is one way to make assumptions on a distribution. We played a lot with the number of parameters that are needed in order to represent a distribution. We played also a lot with how to use the independence assumptions, right? How to write down the probability of events or the probability of the joint distribution given these independence assumptions. And we did that also in the context of three dependent distributions. And the reason I moved to three dependent distributions is that they are simple. The inference algorithms for them are tractable. And there's a nice, cool learning algorithm that is essentially a closed form algorithm to induce three dependent distribution. If you want to induce general form Bayes nets, it's essentially a very big search problem that really is guided by various heuristics, not as clean and nice as in the case of three dependent distribution. So that's what we did actually yesterday when we talked about both inference in three dependent distributions and how to find the most likely distribution. We solved several problems. First of all, we solved the simple problem of here are three options. Which one is most likely to have generated this specific data set? And the reason is that I hope that you're comfortable with computing likelihood, with understanding the notion of most likely and so on. And then we derive an algorithm that is the Chow-Lu algorithm for inducing three dependent distributions. Okay, so now I want to address one question that was asked about naive Bayes as a two-layer three-dependent distribution. And meanwhile, hopefully you guys can think about additional questions that you want to ask. So I think I'm going to move back to just show a slide that better shows this, I think. That it's easier to talk about. Let's see. Yeah, okay. Let's look at this slide. So this is a representation of a distribution. It's a three-dependent distribution in the sense that we have a tree here. The generative model is generate y as a function of what y is, generate x1 according to p of x1 given y, generate x2 according to p of x2 given y, and so on. So it's a tree-dependent distribution. On the other hand, it's also the same model that we used when we talked about naive Bayes. In the case of naive Bayes, all we cared about was predict y given x1, x2, x3, xn. So we cared about one specific event, p of y given x1, x2, x3, xn. But you have all the probabilities to compute every event. And we show this, I think, here, right? So what I showed in this slide is that every event that you care about, you can compute once you have the naive Bayes probabilities, right? Once you have these probabilities, p of xi given y, and of course, p of y, which we call the prior in the context of naive Bayes. If you have these, you can compute, for example, the probability of this event, p of x1, x2, and y. So essentially, this is a tree-dependent distribution. We did not use all the power of it when we talked about naive Bayes. We just talked about how to compute p of y, but you can do everything. Does this answer the question? Okay, good. So let's see if there are any other questions here on any of the things that I mentioned or things that I haven't mentioned.
Hi, Professor.
Hi.
But in the tree independent distribution situation, we do not know the label, but in the naive Bayes, we know the label. So does it mean there's still a difference between each other?
So in all cases, so let's see. So what happens in naive Bayes? What is the learning scenario of naive Bayes? What is the input that you get? The examples are n plus 1 tuples in the notations that I have here, right? So x1, x2, x3, xn, and y, right? So each example is an n plus 1 tuple. And what are you doing with these tuples? First of all, you compute p of y, right? So let's say it's binary. So you compute p of y being 1 and p of y being 0 from the data that you have. And then, again, from the data that you have, you compute p of x1 given y, and then p of x2 given y, and so on. Let me do it here. Oh, okay. Let me bring up another set of slides so this would be clearer. Yeah, so this is what we did when we did naive Bayes, right? The examples, you can look here at the top right, is x1, x2, xk, and then a label. This is the y. And given these examples, what did we do? We computed, first of all, the prior, we called it. which is the P of y. In this case, it's P of n and P of v. It's P of y being n and P of y being v. And then all the conditional probability that we need, right? That's what we did. And once we have this, we can compute the probability of a label given an example, which we factor this way. That's the naive Bayes thing. In the case of tree-dependent distributions, we're going to do exactly the same thing. We're going to learn it in general in a slightly different way. So let's again, the input is the same input. The input is n plus 1 tuples, right? So you get x1, x2, x3, xn, and y, n plus 1 variables. What is the learning algorithm? Let's just revisit the learning algorithm. So you're computing P of xi and P of y in all cases. And then you're computing all the pairwise. So you're looking at y and xi, y and x1 and y and x1 and y and x3 and so on, y and xn. But in the general case, you are also going to look at x1 and x2, x2 and x3, and so on, if you run the Chow-Lu algorithm completely. Now, at the end, you're going to generate a tree. The tree is going to have n edges, just like this shallow tree that we see here for the naive Bayes. Because I have n plus 1 variable, so it's going to have n edges. Which edges are going to be there, I don't know. But here we are assuming that the edges that are going to remain are those that connect y to the xi's. So this is one instance of the tree. But other than that, it's really the same structure. So once you generate, let's assume this comes up to be the spanning tree, then you place on the edges these conditional probabilities, just like Chow-Lu algorithm tells you to do, and you go back to the naive Bayes architecture.
Okay, gotcha. So the naive Bayes is just the one specific case of the tree dependent distribution.
Exactly.
Okay.
Now notice that when we talked about naive Bayes, we didn't know about tree dependent distribution, and we only focused on one event. We only focused on the event P of y given x1, x2, x3, xn.
Mm-hmm.
Only later we realized that actually with the same information, we are more powerful. We can compute the probability of other events.
Oh, okay.
But it is a special case. It's just a tree-dependent distribution.
Okay, gotcha. Thanks.
Other questions? Okay, if there are no questions, we're going to stop here. We are going to keep office hours next week. So if you do have questions, please come. You can definitely use Piazza to ask questions. Other than that, I know this wasn't an easy semester, not for you, not for most of the TAs, not for me, but we made it. So hopefully you enjoy this. Enjoy the next week, and I guess I'll see you all next Friday.
Thank you.
Thanks so much.
Thanks. You're welcome.
Thanks, Professor Roth.
Thanks a lot.
Bye-bye.
Thank you.